Okay, so this is the first video for section 8.6 where we discuss the likelihood ratio test, the LRT. So you pause, copy, play. Okay, so LRT, the likelihood ratio test, is another way to test hypotheses, all right? And it incorporates significance levels alpha, all right? So the likelihood ratio test, the idea behind it is it's going to compare the likelihood of the data under the null hypothesis to the likelihood of the data under the alternate hypothesis via a ratio. The likelihood of the data under the null hypothesis divided by the likelihood of the data under the alternate hypothesis, where L is a likelihood function that we use for the maximum likelihood estimation, the MLE, that helps us find population parameter. Excuse me. Now in MLE, we took the natural log of the likelihood function and differentiated that, okay? We're just going to take the likelihood functions here, top and bottom, okay? All right, so to use the likelihood ratio test, at least the initial version of it, we need hypotheses that are simple. So let's define that. We say a hypothesis is simple if it completely specifies the distribution of the population. Otherwise, we say the hypothesis is composite. So, for example, if we knew that the population was normal with an unknown mean, but a standard deviation of 4, then a null hypothesis or an alternate hypothesis stating that mu is equal to 10 or 3 or 8 is a simple hypothesis, because if it states that mu is 10, I now know everything about the distribution. It's n10 4 squared, okay? If, however, I had the population was mu sigma squared, where I didn't know either mu or sigma, then mu equals 10 would not completely specify the population. And it would be composite because I still wouldn't know the standard deviation or the variance. Okay. All right. And in the next slide, we'll see why this simple hypothesis requirement is important. Okay. So here's the likelihood ratio test. Why don't you pause, copy, and play? All right. So when the null hypothesis and the alternate hypothesis are both simple, that means under both hypotheses, we know exactly what the population is, what the distribution is. So let's just suppose that the null hypothesis is the parameter theta is equal to theta 0, and the alternate hypothesis is the population parameter theta is equal to theta sub a. We create the likelihood ratio statistic. So that's the likelihood of theta 0 divided by the likelihood of theta a, which means it's the likelihood of theta 0 given the data x1 through xn divided by the likelihood function of parameter theta a given the data x1 through xn, all right? So those are going to be products of probabilities, the probability of x1 under theta 0 times probability of x2 under theta 0 times probability divided by the same thing with theta sub a instead of theta sub 0, okay? Now, we can't calculate any of those probabilities if the hypotheses aren't simple. So if it wasn't a simple hypothesis, then simply stating the parameters theta 0 doesn't give us enough information to calculate the probability of data point x1, given that theta is equal to theta sub 0, right? So I wouldn't be able to calculate that probability, and hence the likelihood function I wouldn't be able to necessarily calculate as a value, a numerical number, right? So I would have, if the hypotheses weren't simple, this ratio would not be an actual number, okay? But if it is simple, once I specify theta 0, I have the entire distribution, and I can calculate the probability of x1 given that theta 0 as a number times probability of x2 given that theta 0 as a number. So I get a bunch of numbers. I get an actual numerical value coming out here. Okay. All right. Well, then the likelihood ratio test rejects the null hypothesis if this ratio, this t, is small, less than or equal to c. That should make sense. If it turns out that h sub 0 is false, the likelihood of the null hypothesis should be much smaller than the likelihood of the alternate hypothesis, and thus this fraction should be small, right? If the null hypothesis is true, we would hope the likelihood function of theta 0 is large compared to the likelihood of the alternate hypothesis, and thus this fraction would be large. Okay, so we're going to reject the null hypothesis when that ratio, that t value, is small, less than or equal to some c, and that c value is going to be chosen based upon a desired significance level or type 1 error rate alpha. Okay, all right, let's go do an example. Okay, so here's an example, mostly. Pause, copy, and away we go. All right, so in example 8.20, we have a distribution that's exponential with unknown parameter lambda, and I've got 9 data points from it. I've got a random sample of 9 points from that distribution. I have 2 simple hypotheses. Lambda is 8 versus lambda is 10. And once I specify lambda, I know everything there is to know about that distribution, and I can calculate probabilities, right? By the way, the PDF of an exponential distribution with parameter lambda is that bad boy, okay? So I am going to calculate the t value here. So I'm going to calculate the likelihood that lambda is 8 divided by the likelihood that lambda is 10. The likelihood that lambda is 8, well, for x1, the probability of x1 would be 8 times e to the negative 8 times x1. Then I'd multiply it by the same expression for x2, 8 times e to the negative 8 times x2, et cetera, all the way up through 9. Likelihood for lambda being 10 is exactly the same thing, but the 8s get replaced by 10s. Okay, so I get that fraction, that ratio. Simplification. Well, this is a product, so I've got 8 of these. Sorry, I have 9 of these 8s multiplied together, so that's 8 to the 9th. I've got 9 of these 10s multiplied together. And then if I multiply a bunch of e to powers together, I can mush the powers together under addition. So I have e to the negative 8, which can get dragged out, times the sum of the xi's. So instead of multiplying e's together, I'm going to add their powers together over a single e. Drag the negative 8 out, same story down below. 8 over 9, 10 over 9, simplify it to 0.8 to the 9th. And these two guys, if I subtract the top power minus the bottom power, I get positive 2 copies of the sum of the xi's, right? So the likelihood ratio test says we're going to reject the null hypothesis if that ratio is less than some threshold c. Now, I'm going to solve for the sum of xi's, so I skipped the algebra, but you should just check to make sure I didn't skip the algebra. I solved this for the sum of the xi's by dividing both sides by 0.8 to the 9th. That becomes 1.25 to the 9th. Taking the natural log of both sides, there it is, and then dividing the 2 to the other side, there it is, okay? So we're going to reject the null hypothesis when the sum of the xi's, the data, sums up to something less than what I'm going to call C2, okay? So the critical region is the set of all data points whose sum is less than C2. By the way, each of the data points is greater than or equal to 0 because it's an exponential distribution. Okay, so how do we go about figuring out that C2? Okay, well, we need to set the significance level. So let's set alpha to be 0.05. That's the probability I make a type 1 error where I reject the null hypothesis when it was actually correct and true. So I decide I'm comfortable with that mistake 5% of the time. Okay, well, under the null hypothesis, my data is exponential lambda equals 8. That means the sum of 9 exponential 8s turns out to be a gamma distribution with parameters 9 and 8. Okay, that's a math 313. And on the one of the first assignments was to copy down all significant results about lambda distributions. That was one of them. A sum of independent and identical exponential distributions, say gamma distribution. Sorry, I said a lambda distribution, a gamma distribution. So that's a 313 result. Now, I'm going to be comfortable making a mistake 5% of the time. So if I look at the 5% quantile of the gamma distribution with parameters 9 and 8, I get 0.5869. I did that via R code. Check in the notebook under 8.20, you should see the code for that. And that's my value, C2. Because 5% of the time, I want to have the sum be less than C2, even though the data came from exponential 8, right? So that's my C2. So my test is I'm going to reject the null hypothesis if the sum of my data is less than 0.586. And that's via the likelihood ratio test. Okay, we use the likelihood ratio and a pre-specified alpha value to get that test value. All right, let's see the value of this test. Last slide. All right, it turns out the likelihood ratio test in some sense is the best possible test for hypotheses. Best possible test. So pause, copy, play. Okay, so likelihood ratio test in some sense is the best possible test for comparing simple null versus the simple alternate hypothesis. They both have to be simple, okay? So, and the reason for that is the Neyman-Pearson lemma, sorry. So let's say I have a random sample of n data points from a distribution that has parameter theta. It's only one parameter. And we wish to test two simple hypotheses where the parameters theta 0 versus the parameters theta sub a, okay? Now, we know the likelihood ratio test tells us to reject the null hypothesis if that ratio of likelihoods satisfies t being less than c, where c was determined via some significance level of alpha, okay? So nothing special there, just sort of a summary of the likelihood ratio test. Here is the cool result that tells us the likelihood ratio test is the best test, okay? All right, if you come up with any other statistical test with a significance level that's alpha or smaller, then that other statistical test will have a power that's less than or equal to the power of the likelihood ratio test. And remember, we like big power. Power is the probability that I correctly reject the null hypothesis when it's not correct, all right? So I'd like that power to be as large as possible, as close to 1 as possible, right? So if you come up with another test that has the same significance level or less than the likelihood ratio test, its power will also be less or equal to the power of the likelihood ratio test. So in a sense, for a fixed significance level, the likelihood ratio test maximizes the power. No other test will have a higher power than likelihood ratio test, all right? And maximizing the power means we're minimizing the probability of making a type 2 error. So the likelihood ratio test, if you fix the alpha, it's going to give you the test with the best power result, okay? And that's the best test we can have.